すいません。あ、もう。
Explore the implications of what our concepts about the real world are. So to a certain extent, the spirit of theoretical physics can be cast into the words of Wittgenstein, who said what we cannot speak about clearly, that we must pass over in silence. Well, so indeed, we have concepts about the real world, and it's not possible to cast them into a precise mathematical form. That usually is an indicator that some aspects of these concepts have not been well understood. So theoretical physics aims at casting these concepts into mathematical language. But then mathematics is just that, it's just a language. And if we want to extract physical conclusions from this formulation, we must interpret the language. And that's not the purpose or the task of mathematics, that's the task of physicists. That is where it gets difficult again. But again, mathematics is just a language. And to again use Wittgenstein, he says the theorems of mathematics all say the same, namely nothing. Okay? And so what does he mean by that? Well, obviously, it doesn't mean that mathematics is useless. It just refers to the fact that if we have a theorem of the type A, if and only if B, A and B being propositions, then obviously B says nothing else than A does. And A says nothing else than B does. It's a tautology. Okay? Now, of course, mathematically, logically, it's a tautology, but psychologically, or for understanding of A, it may be very useful to have a reformulation of A in terms of B. Right? So, with this understanding that the mathematics just gives us a language for what we want to do, the idea of this course is to provide proper language for theoretical physics, and certainly for the 4 courses you have heard so far. So the aims of the course, or the overarching aim, is to provide proper mathematical language for classical mechanics, electromagnetism, quantum mechanics, and statistical physics. Now, so these subjects you studied in the module TP1 to TP4 here at Erlangen or at many other universities. And obviously, we're not going to revise all the mathematics that are needed for these 4 subjects, but rather we will develop mathematics from a higher point of view that we can now approach that you have some prior knowledge of these subjects. And so far, we have certainly used a fair amount of analysis in order to study these subjects. Further, a fair amount of algebra, mainly linear algebra, but also nonlinear algebra at times, and geometry in one or the other form. So very often in classical mechanics you would appeal to geometric intuition in setting up a problem or finding the solution to a problem. The same goes for electromagnetism. Algebra you mainly use in quantum mechanics, that's the modern way to do quantum mechanics by means of linear algebra, and in statistical physics you use some geometry, maybe without really realizing it, by looking at convex cones of states and so on. Now if you take these 4 fields and you try to be pedagogic about it, you draw circles around them. And so classical mechanics and electrodynamics certainly use a fair amount of analysis and geometry, and so does general relativity for those of you who took that course or are about to take it. Well, quantum mechanics lies certainly well in the intersection of analysis and algebra, which we call functional analysis. And, well, algebra and geometry, let's do statistical physics justice, it more or less lies there. Of course, this is not a pure picture. This is mainly where the intersections of these fields come to play. And here in the middle, where these 3 fields intersect, we have differential geometry as a mathematical subject, and it's differential geometry that this course is mainly about. So the mathematics of this course will be that part of the mathematics of these different theoretical subjects where these 3 fields intersect. That's the rough idea of this course. Now, the structure of this course and indeed the development of differential geometry that we're about to start starts, well, with sets. So we'll talk about set theory, because any space in classical mechanics, the space of configurations, or the phase space, in electromagnetism, the space over which you work, or in quantum mechanics, the physical space over which you construct your Hilbert space, and so on, all these spaces are certainly sets of points. That's the coarsest structure of such a space. It is a set. But what precisely is a set? Well, one can delude oneself into thinking one understands a set by saying a set is a collection of elements. But that just raises the question what a collection is and what elements are. So we certainly need to do better, and there is a fundamental problem if we start writing a book about mathematics whose pages are all empty yet. Because what could the first definition be? For definition, you need notions that you already have in order to define a new notion. But if you don't have any notions yet, how do you start? Well, the trick is to start axiomatically, and so we'll have to write down axiomatic set theory. But that then raises the question, in what language would you possibly do that? So actually, before we come to set theory, we need another building block down here, and that would be logic. And we will deal with propositional and predicate logic first. That will define our language, and then we'll be able to write down the axioms of set theory. Now, once we have the axioms of set theory and we have our beautiful sets, the question is, what can we do with them? And one thing we certainly need, at least for these 4 subjects, we need a notion of continuity. For instance, in classical mechanics, famously, particles don't jump. So the particle trajectory doesn't stop somewhere and start somewhere else again. It's continuous. So you need a notion of continuity, and such a notion you get by distinguishing certain subsets of the basic set you have, and that leads to the notion of topology. So we'll deal with topological spaces and all the notions associated with that. Now, there's an abundance of topological spaces, such an abundance that you cannot even classify them. And so we will need to restrict somewhat to interesting topological spaces. Well, topologists may disagree that only those I'm going to write down are the interesting ones, but from the point of view of theoretical physics, immediately interesting are the topological manifolds. Topological manifolds, which we're going to define, are topological spaces that locally, around a point, look like some r to the d. Now, that's not enough. If you have topological manifolds, you also need, in physics, especially in classical physics, you need a notion of derivative. You need to be able to talk about the velocity of a curve. And that cannot be done in topological manifolds. What you need there, you need differentiable manifolds. And that's an entirely new beast, and there we will need to introduce the technology of charts, and the technology of charts will for the first time make contact to much of the formalism you already used in the standard courses. In fact, all the standard courses have been formulated in charts so far. What's a chart? I explain later. A chart is like a sailor uses a chart of the world to travel across the globe, And if you want to know where you are and where you want to stay, you take out your atlas. In the atlas, you'll turn the pages and you find the appropriate chart around the point where you are in the real world. You can navigate in the chart. And the chart should be a one-to-one picture of the world locally. Because if you then move in the world such that the chart would leave the page, you better turn the page and you find the other page that slightly overlaps with the chart in the atlas, so that you can then navigate on with the other chart. And very much the same thing, looking for another chart that overlaps and understanding how... in this case. That's right. Okay, so we'll certainly come to that. Now, once we have differentiable manifolds, maybe already before, we'll come to a notion which, well, in some sense, is yet another structure, but it's bundles. So the idea of bundles is you take a manifold, and you take another manifold, and to each point of a given manifold, you attach the other manifold. You build a bundle. You have a vector bundle where at each point you attach a tensor space, and so on. And bundles are a very important concept in geometry, in differential geometry, and indeed much of modern physics can be understood or can be cast into the language of bundles. So it's true for particle physics, but also for gravity, and so on, certainly for quantum mechanics. So actually about already here, we will learn that the notion of position vector should be forbidden. There is no such thing as a position vector. Doesn't matter how often it's repeated, there is no such notion. Now, in bundles you learn there's no such thing as a wave function in quantum mechanics. You get away with the notion of position vector unless you look too closely, and then it fails. And the same is true in quantum mechanics. You get away with the notion of wave function, but then it fails. In fact, the wave function is, a position vector is just a collection of coordinates, but they do not constitute a vector. And the wave function in quantum mechanics is not a function at all. It's a section in a complex line bundle over the physical space. We cannot understand this, but we will at the end of the course. So these notions are needed if you really want to say what's going on. Now, okay, so once we have bundles, or maybe also alternatives to bundles sometimes, so don't take the picture too seriously, it's a rough idea of how this building is constructed, we'll have geometry. Geometry comes in the form of so-called tensor fields on this structure, so that could be symplectic geometry, that would be the geometry of classical phase space in mechanics, but actually it's a much bigger subject because for virtually all dynamical systems of interest to us, the phase space is equipped with the symplectic geometry. There may be a metric geometry. This is certainly the case in electromagnetism. To a certain extent, the geometry is just in the volume form. And certainly it's the case in relativity, and especially in general relativity, you need a so-called Lorentzian metric. This is a structure that sits on top here, but you need to understand more. With logic. So chapter 1 is actually already axiomatic set theory. And the first section here is...
Just really question behind the logic behind this. You said the logic comes first before that.
Yes, and the logic behind the logic is that now the first subsection will be propositional logic. So I summarize the logic under axiomatic set theory because it's the language for axiomatic set theory. So 1.1 is propositional logic. Now, the key notion of propositional logic is a proposition. Definition, a proposition, P, small p, is, well, let's call it a variable, whatever that means. It's a variable that can take the values true or false. no others. That's a proposition from the point of view of propositional logic. So in particular, it is not the task of propositional logic to decide whether a complex statement of the form there is extraterrestrial life is true or not. That's not the task of propositional logic. Propositional logic already deals with the complete proposition and just assumes it's either true or false. You can say, well, let this proposition have the value true. Yeah, you can do that. But if nothing is said, it's either one, not true at the same time, of course, no other is true or false. You know this. It's also not the task of propositional logic to decide whether a complex proposition of the type in winter is colder than outside. Well, this is a proposition at all. Well, obviously the one I just mentioned doesn't seem particularly reasonable, but it's not the task of propositional logic to decide. It's important to realize this. Okay. Propositional logic deals as its atomic, elementary notion with the notion of propositions. Now, certainly, you can build new propositions from old ones. Or from given ones. And one does so with the help of logical operators. And they come in different forms, and the simplest form is unary operators. And there are 4 unary operators. What's a unary operator? A unary operator takes one proposition, P, and makes from it a new proposition. So the one that's given in the unary means you take one proposition as given, you construct new ones, and of course this one proposition can have values true or false. Now, I said there are 4 unary operators. Let's write them down. Well, the famous one is the not operation, not P. Not P is, again, a new proposition. A proposition called not P. And this proposition, if P takes the value true, this proposition takes the value false, and if P is false, this proposition takes the value true.